Hello, we're going to do another example, this time using that formula dF equals I dL cross B for finding the force on a segment of wire whose length is dL carrying a current I parallel to the vector dL, and it's immersed in a uniform magnetic field, or at least a magnetic field that doesn't change appreciably over the size dL. So I'm going to work an example that's going to actually require a little bit more calculus and sometimes give students a problem. So let's get started. Let me switch to the document cam. So in this case, I'm trying to just show you the original problem. So what we're looking at here is basically a current carrying wire comes up, goes into a half circle of radius r. Then at the end of that half circle creates another half circle of radius r. Then at the end of that circle creates another half circle of radius r, and then shoots back out. Notice the length of these little straight segments is r. The magnetic field is represented by these little green circles with dots in them. Remember, a circle with a dot in the middle means it's coming out. So I've created just for this particular part of the problem where we're doing this, because we're going to get a result here that's the same as what you'll get here, is the same as what you'll get here. So I've chosen a coordinate system that helps me there. Specifically, I've chosen the x-axis pointing down this way, the y-axis pointing this way, and using your right-hand rule, the I vector crossed with j, which points this way, gives you k pointing out. So this is clearly a magnetic field pointing in the k direction. I'm pretending the magnetic field has a magnitude of b, just plain b. And of course, since it points in the z direction, it's in the k hat direction. You might actually imagine this as maybe the warming mechanism of a hot plate. You could actually have wire come in, and of course you want the hot plate to be fairly warm everywhere. You use a fairly good conductive metal, heat conductive metal here, and you run a current through, say, tungsten or something like that, that would heat up as well, and then that would actually provide a pretty good amount of heat. But you might want to find out what the magnetic field is doing, what's it actually causing in terms of forces on these particular wire segments. So what we're going to do is trying to find the net force on this wire, which is a straight wire, a semicircle, a semicircle, a semicircle, and a straight wire. Okay. To do that, we're going to use the expression dF, the differential force, is equal to I dL cross B. Again, the assumption being that B doesn't change very much over the size dL, and that dL, of course, is a line segment that actually points in the same direction that the current flows. Then you'll get the differential force dF. So we're going to integrate that so that the integral of dF is actually equal to F. Okay. So I've drawn this diagram and I've taken the time to work some things out. The hardest part really is going to be the semicircle, and I'll do one semicircle, and then from symmetry I can tell, well, this is just like it and this is just like it, so I can just add those forces up or whatever once I find out what the forces do to this one. This one right here, of course, we know is just F equals Bill because it's a straight line segment. So in that case, F equals Bill, and of course the angle between the magnetic field and the actual current carrying wire is 90 degrees, and the sine of 90 is 1. So let's call this F sub R, meaning the right-hand side. And notice it's I times L. So if I make my L vector pointing in the direction of the current, and then I turn my hand so that my fingers can curl towards B, which is like this. So now B is pointing up, of course. Then my thumb points that way. So I see that this particular force is equal to B times I times R. And it actually points to what this is called our J direction. So that'll be J hat. So just using that coordinate system as if I'm going to use the whole thing all over. So that's that one. If we look here, we've got dL going downward. So my pinky's in the direction of that. This is a good chance for us to use our setup like this, where the index finger points in the direction of the current, the middle finger points in the direction of the magnetic field, and the thumb points in the direction of the force. So in this case, we see the magnetic field's got to point up this way, and that's actually going to force us, magnetic field pointing up, current pointing down, and of course we get the force pointing to the left. So in this case, F left is equal to BIR in the negative J hat direction. So you can see FL plus FR is just going to cancel out. So those two get a net force of nothing. Now let's attack the semicircle. So the reason I drew the x-axis this way and the y-axis this way is because we already have a coordinate system that's defined in terms of this. You might not know it. You might not have worked with polar coordinates before, but cylindrical or polar coordinates are quite nice. This is cylindrical coordinates. Polar would just be the two-dimensional part of it. But we have to use the k vector, which points out of the page, so that makes it cylindrical coordinates. So what I have is an x-axis here, a y-axis here, and I just chose an arbitrary point. I usually choose that point in the first quadrant just to keep things from getting complicated. And I've chosen on the wire, and of course I'm going to let the angle theta, which is the counterclockwise angle from the positive x-axis, up to the radial line. So here's the radius r. Theta goes up to the bottom of it. If you allow theta to change by an amount d theta, which is what that shows right there, then you'll get a little line segment about that long. I drew it here bigger just to, notice I said vector exaggerated. I drew it here bigger just to make sure you could see what I was talking about. Now that line segment from s equals r times theta, remember that from trigonometry, arc length is equal to r times theta, where theta is in radians. In fact, that was the definition of radians to some extent. So using that, I could say, well, the dl, the length of this little unit vector, or not unit vector, this little differential vector should be r times the change in angle, which is d theta. But I want to give it a vector, so I call that vector theta hat. Because notice it actually points, it's always parallel to the surface of the circle, or the circumference of the circle, and it points in the direction of increasing theta. So I just call it theta hat, and that is actually a vector. I'm going to work that out in a second. Not only that, if you pointed one parallel to the radial line, which goes from the origin out, that would be called r hat. And again, the hats, remember, are just indicators that they're unit vectors. So with that in mind, I try to zoom in a little bit on what we're looking at over here. And I tilted it around so it made more sense. So you can see here's the little r hat vector, there's a little theta hat vector. That r is at an angle theta. Of course, this little bit is d theta, but that r is at an angle theta, so I can imagine another x-axis, which I call x prime, and realize this r hat is inclined by an angle theta with respect to that x. So I can get the components of the r hat vector. They'd just be cosine theta times I hat. Remember, the length of this is 1. So cosine theta would be adjacent, which is what we're looking for, the x hat, over the hypotenuse, which is 1. So cosine theta would equal the x component over 1. So the x component would just be 1 times cosine theta over 1, which is just cosine theta. The y component, of course, would be given by sine, because the sine of theta is opposite, which would be the y component over hypotenuse, which is 1. So I get sine theta times j hat. Now I can do the same thing working out the theta hat. Notice the theta hat is actually 90 degrees in front of it. So this angle right here between this y prime axis and the theta hat vector is again theta. I can see if I take the cosine this time, I get the actual y component. So cosine theta j hat is one part. Now this part is actually giving me the negative of the x. So I have to take the negative sine of theta times I hat to get the the x component. So theta hat turns out to be negative sine theta I hat plus cosine theta j hat. Now we have what these unit vectors are in terms of thetas and stuff of that sort. So that'll come in handy. Now we have to work out that basically f is equal to the integral of df, which is equal to the integral of I dl crossed with b. So we're just going to work all that out, and it's just, you know, sort of matter of reading it. Well, the I is a constant. I'm going to pull that out in front. And then I'm going to say the integral of dl, which is in fact r d theta, theta hat. That's going to be crossed with b, which I said was b k hat. Okay. Now the r and the b are also constant, so I can pull those out. I'm going to say b I r, just like F equals Bill. So F equals BIR. Another thing to remember, that physicists write this kind of stuff, and it's a little weird for mathematicians or people that just came out of their math class. But just because this is after the d theta, that does not mean it's not integrated. In fact, all this has to be integrated. So now what I got to do is actually work out what theta hat cross k hat is. That's the whole reason I worked out what is r hat and then what is theta hat. In fact, I really didn't have to have r hat. I just did it for completeness. The theta hat is really what I needed. So I got to work all this out and then integrate it, because what we're going to do is we're going to allow theta to run from 0 all the way to pi. That will take into account the entire arc length, and that'll give me the formula for the actual force on this thing. As you might suspect, if you look at I dl cross b, I is going here as well as dl is. If I cross that with b, I do get something sort of pointing out in this general direction. And as you notice, this general direction includes a x component and a y component. When you get over here, that general direction includes a y component and an x component as well, but the x component is actually the negative of what it was over here. So you expect all these x components over here to be exactly equal to all the x components over here, so that your net result is just something in the y direction or the negative y direction, or in the j direction or negative j hat direction. So from symmetry, that's what we expect is going to happen. I want to see if the math works that out as well, but we'll find it all out when we start to evaluate this integration. So I am integrating from theta equals 0 to pi, but I got to work out what theta hat cross k hat is. So let's do that. Theta hat cross k hat is just, I'm going to take my theta hat from over there and say it's negative sine theta I hat plus cosine theta j hat. This is a way that you can actually do cross products without having to do matrices. K hat's just k hat. Now remember, this little coordinate system might help us out a little bit. So if I draw the x-axis pointing out of the page, and then the y-axis horizontal, and then the z-axis pointing up, that is a right-handed coordinate system. And in fact, the I hat points this way, the j hat points this way, and the k hat points this way. This will come in handy when I'm trying to do the cross product this way. And actually, you'll be able to get to where you can do this so fast it won't even matter. So cross product, like a dot product, is what we call a scalar operation. Excuse me, a linear operation, not a scalar operation. So what that means is the scalar in front of all the vectors can just come out in front, and you can just let the vector operations play out. So when I do this using distributive property, I get negative sine theta times I hat cross k hat. And then when I do this times this, again, I'm just going to pull that cosine theta out. I'm going to say plus cosine theta times j hat cross k hat. So I now have negative sine theta times I hat cross k hat plus cosine theta times j hat cross k hat. But check this out, I hat cross k hat. I hat, so I'd imagine my right pinky pointing out of the page, and then I have to put, of course, my palm up so that my fingers can curl towards the k hat direction. And when I did that, I'd actually get my thumb pointing in the negative j hat direction. So this quantity right here is negative j hat. Now there's a lot of different ways you can come up with these things, but I say just imagine this, use your right hand. Don't forget, because you're writing with your right hand and you accidentally use your left hand, that's going to give you the wrong result. So always use your right hand, or at least flip the result for left. But there's a lot of different ways, like I said, and you could have put this in a matrix and worked it all out, but I thought it'd be a nice opportunity to show you how to do this. Now, j hat cross k hat is another one. Now, in this case, I can actually show it a little easier. So it's j hat. My pinky's pointing parallel to the y-axis. My palm points in the k hat direction. In other words, if you imagine a vector representing my palm by a vector perpendicular to my palm, it points in the b hat, in the k hat or z direction. And also, you can imagine if you want to do the curl thing, you can imagine your fingers curling towards k. And then, of course, my thumb is pointing straight out of the page, because you imagine all three of them have to be mutually perpendicular. So when you get that, you see, oh, okay, it points in the z, or excuse me, out of the page, which is in the x hat direction. So this guy turns out to be, or excuse me, the x direction, which is the I hat direction. So this one's just I hat. So now we can go back to our actual integral and start working that out. Again, we got f is equal to b I r times, I'm going to put a little bracket here, integral from theta equals 0 to pi of negative times the negative is going to give me a positive. So I'll say sine theta d theta, and that's of course in the j hat direction. Now I've got the other vector, the other part of the vector, which is plus the integral theta equals 0 to pi again. Now this time it's going to be cosine theta d theta in the I hat direction. Now we already argued that the i's are probably going to disappear because this force vector, which points radially outward, has a positive x component here and a negative x component over here, and by symmetry you expect them to cancel out. Well, you can see that right here as well, just remembering that the cosine graph looks like this. If this is pi, cosine graph looks like this from 0 to pi. And you see that there's exactly as much area in the positive side as there is in the negative side. When you look at the same thing for sine, if this is pi, and you get like that, you see, no, that's all positive. So right now you can see if I integrate cosine theta from 0 to pi, I'm going to get actually 0. Another way you can think about it is, okay, the integral of cosine is actually sine because the derivative of sine is cosine. So I'd get the integral of sine, or the integral of cosine is sine. So then I take the sine of pi, which is 0, and I subtract from it the sine of 0, which is 0. So I'm clearly going to get 0. So there's a lot of different ways we can see that this component is in fact going to 0. So now our integral has become this really simple thing, the integral of sine theta d theta, and it gives us a result in the j hat direction. So I now have that f is equal to b I r times the integral from theta equals 0 to pi of sine theta d theta in the j hat direction, which is actually equal to the negative cosine. So I'm going to put the negative out in front and say b I r times cosine theta, and that's going to be evaluated from 0 to pi, and that's going to be in the j hat direction. So I get negative b I r. Now the cosine of pi is negative 1. I have to subtract from that the cosine of 0, which is 1, and then the j hat's going to be there. So I get negative 1 minus 1 would be negative 2 times negative 1 would be positive. So I'm going to say finally the total force on that guy is equal to positive 2 b I r j hat. Now that's just due to this one. Notice it points this way from the center out along the symmetry axis. So up here I'm going to get the exact same thing. It's just going to point up here. So I will call this force RS for R8 semicircle. The force for the top I'm going to call T. That's going to be, and I wrote this like a Z, that is a 2 though. I hope I said it that way. This is also going to be a 2BIR, but this one's actually going to point along the symmetry axis and point upward, which we call that the negative, according to this axis. Positive x is pointing down, so negative x will be pointing up. So I'm going to say negative I hat. And then there's another one for the force on the left semicircle. Now this one, out of symmetry, again, is going to be pointing this way. Notice it goes from the center through the symmetry axis. Okay, so that force should be pointing that way. So that one's going to be, in fact, negative 2BIR. And that way, of course, according to this coordinate system, is the negative j hat direction. So that's why I put the negative there. And then, of course, we also have the force left plus force right. Force left is negative BIR j hat. And force right, force right is positive BIR j hat. So when we add all these up, the total force, this one and this one cancel each other out, and this one cancel each other out. So all we're left with is the force from the top one, which in fact points upward. So I'll just write it this way. It's equal to 2BIR upward. That way it's not tied to any weird coordinate system that I made. And I'll just say upwards like this. So that's it. That's a very typical problem. You can see, examples like this in your book. In some cases more complicated, in other cases less complicated. And often authors try to avoid, introducing like a theta hat and phi hat and stuff like that. I say just run with it, make use of the tools as they are. As long as someone explains it to you, you're good to go. So that is the actual force on this heating element, if you will. It turns out to just be 2BIR pointing that way. 2 times B times I times R, where B is the strength of the magnetic field that it's immersed in, I is the current going through it, and R is the radius of these little semicircles, which also happens to be the length of these little legs. But it turns out this one and this one canceled each other out. This force and this force canceled each other out. The only one that really mattered was this one, which was pulling us upward. Well, I hope that helps you see a little bit how this is done. And again, there's the answer at 2BIR upward. There's the original problem. And that's it.